There are two ways to eliminate this inactive core. One is to scoop it out, that's called hollowing. And the other is tapering, because that's the material that's left if you eliminate what was painted here with chalk. So that's what is left, and that's the rest of it is here. And then you bring the tip, you snap it together to get useful. Then design number 2 is will be here. Design number 2 is the hollow tube. I draw it this way. And because we know the method, I'll go fast through the steps that are detailed in the book. Here is the load P. This is the substrate. And the deformation is here. And the cross section is an annulus of a diameter D2 and thickness T2. And right away you see a drawing with 3 dimensions. And those are the length, the diameter, and the wall thickness. The way to be happy in this domain of asking questions and then answering them is, I said it many times, is to try the simplest first. And the simplest is not to juggle 3 balls at the same time. It's simpler to juggle only 2. And we juggle 2 in design number 1. And in fact, it's a very good idea to think about proceeding more simply. In fact, in practice, meaning manufacturers of tubes have, because the tubes have a purpose, they are being bought. The tubes that tend to be bought are those that have cross sections that are geometrically similar. Which, in other words, if the small one looks like this, then the bigger one will be both with a bigger D and bigger T, you know. And so we make an assumption that all cross sections, regardless of size, are geometrically similar, which means that that T, in our case T2, over the radius, in our case D2/2, is a small number, epsilon, actually order of magnitude smaller than 1. So epsilon is a characteristic that defines the existence of a class of tubes you buy from the store, small and big. Next time you're in the machine shop, you can look at some of these tubes. They tend to be this way. In fact, they're this way all the way to, there must be a reason other than the cost, all the way to the tubes used for sewage in the city. All right, by the way, those two must withstand the loading that's transversal to the tube, even though the tube is buried underground. Yeah. All right. Well, think about it. So the problem is, what is the volume? Well, the volume is the cross-sectional area of the annulus, which is pi d2 times L2, and then times this thickness called T2. And that's the same as pi epsilon, and then the result here is pi epsilon over 2, and then what I have written L2 d2 squared. Yeah, anyway, so that's the object of the game, or the unknown, let's put it this way. And we get to it with two formulas. The one that comes from the distribution of stresses, called the Roman 1. And I'll just write it down the way it is in the textbook. For that, we get that the maximum allowable stress in this design, just like in the first one, this is design number 2, the maximum allowable stress will happen at the north pole and south pole of the cross section that touches the wall. And so for Roman 1, the formula is SMA equals PL2 and then over I2. This is the area moment of inertia of the annulus times d2 over 2. For I2, you can do the integral yourselves or look it up in your, I hope you have a textbook about strength of materials. The formula for this thing is pi times the radius to power 3 times P2, which means pi epsilon and then R2 to power 4. So that's one formula relating D2 and L2. In other words, from here, you know that you need L2 and D2. So you have one relation. The second relation comes from the formula for delta, which turns out to be PL2 cubed over 3EI2. And again, you have I2 here. And you have therefore another relation between L2 and D2. And all of this from the system, you get L2 and D2, and then substitute in this expression for the volume, and that move takes you to the punchline, which is that the volume of this second design, I write it here, is 6 of these units. And then SMA squared. Now, there are several comments worth remembering. One is that reducing the expenditure by a factor of, to half of what it was is a big deal, very big deal. The personal version of that is a little bit different. It is how easy it is to make a discovery that's substantial by simply asking about the freedom that you have to change the drawing. It's almost effortless. You don't have to go in the shop and build one thing and test it, and build another thing and test it. By the way, the Wright brothers, who made the first manned flight, were tinkerers, and in their shop they built many things and tested them Originally, they were making bicycles and making sure that their bicycles were better than other people's bicycles. And then they built an airplane, meaning the wings and everything, after having tested the components. But they built many components with many sizes and shapes before deciding which designs to use for strength and for lightness. Get it? That wasn't what we've done here. Here we simply asked, can we change the drawing? And the rest was fun.